Howdy students. In this video we're going to discuss a new concept, climate sensitivity. Climate sensitivity is a metric that tells you how sensitive the climate is to greenhouse gases added to the atmosphere. A high climate sensitivity means you get a lot of warming if you add greenhouse gases to the atmosphere, while a low value means you don't get that much. Because of this, climate sensitivity is often viewed as one of the most important parameters in climate science. There are different definitions of climate sensitivity, but one that we'll start with is that the climate sensitivity is the amount of warming you get if you apply 1 watt per square meter of radiative forcing to the planet, and then you let the system run to a new equilibrium. We can estimate this by starting with the zero-layer model using values of solar constant albedo for the Earth. We have worked this out previously, and we know that energy in and energy out are both 238 watts per square meter, which tells us that the surface temperature is 254.54 Kelvin. In the past, we just rounded this to 255 Kelvin, but we need more digits of precision here. So now, let's increase energy in to 239 watts per square meter. After the planet reaches a new equilibrium, energy out will also be 239, and the surface temperature will therefore be 254.80 degrees Kelvin. In other words, if we apply a radiative forcing of 1 watt per square meter to the planet, then the surface temperature of the planet will increase by 0.27 degrees Kelvin. So this is our first estimate of climate sensitivity, 0.27 degrees Kelvin per watt per square meter of radiative forcing. However, this is an awkward unit. Because of that, climate sensitivity is frequently expressed as the response to doubled carbon dioxide. Doubled carbon dioxide has a radiative forcing of about 4 watts per square meter. So we can multiply our value of 0.27 degrees Kelvin per watt per square meter by 4 watts per square meter to get the climate sensitivity. Note that watts per square meter cancels, so that the climate sensitivity expressed in this unit, the warming from doubled carbon dioxide, is 1.1 degrees Kelvin. So that's pretty simple, right? And now, your moment of...
Wait. You haven't talked about feedbacks at all.
Oh, right. We have not done that yet. It turns out that as the climate warms, things on the planet change. For example, we know that ice melts reliably at 0 degrees Celsius. As the climate warms, less of the planet is cold enough to be covered by ice, and the amount of ice on the planet therefore decreases. This video shows the decrease in sea ice as the polar region warms up during the summer of 2013. In Chapter 2, we showed how the long-term warming trend was driving a long-term decrease in sea ice in the Arctic, as well as causing other forms of ice, such as glaciers and the big ice sheets, to melt. This has important consequences for the climate. Because ice is bright white, when it melts, it usually uncovers a darker surface. So as the planet warms and ice melts, that causes the planet to become darker and the albedo to decrease.
This creates what we call a feedback loop. It starts with some radiative forcing, which could be anything from an increase in greenhouse gases to the sun getting brighter. In response, the climate warms. However, this warming melts ice, which decreases the planet's albedo. This leads to more warming, and this additional warming melts even more ice, which leads to even more warming. The net result of this process, known as the Ice-albedo feedback, is that the warming from the initial radiative forcing is amplified by the loss of ice and the resulting decrease in albedo.
There are a number of these feedbacks. Obviously, there's the Ice-albedo feedback, which we just discussed. The most important feedback is known as the water vapor feedback. As the climate warms in response to an initial radiative forcing, The warmer atmosphere is capable of holding more water vapor, so atmospheric humidity increases. Because water vapor is a greenhouse gas, this increase in atmospheric humidity increases the number of layers, N, which our favorite equation tells us leads to additional warming. This then leads to further increases in atmospheric humidity and further warming. A common error that people make is imagining that these feedbacks imply small changes in radiative forcing lead to infinite changes in the climate. This is not correct. Each trip through these feedback loops leads to less warming than the previous trip, so the amplification is finite, and small changes in radiative forcing lead to small changes in the climate's temperature. In addition to the feedbacks we've already discussed, there are two more important feedbacks. The previous feedbacks are positive because they amplify an initial warming, but there are also negative feedbacks which ameliorate an initial warming. An example of this is the lapse rate feedback. This results from the fact that warming of the atmosphere is not uniform, and we expect the upper atmosphere to warm more than the surface. This enhanced warming of the upper atmosphere will lead to enhanced radiation to space, which will offset some of the initial warming. Next is the cloud feedback. Clouds affect the climate in two opposite ways. First, they reflect sunlight back to space, which tends to cool the climate. Second, they absorb infrared radiation emitted by the surface, decreasing energy out just like a greenhouse gas, and this will tend to warm the climate. The net effect of clouds on the climate is therefore the difference between these two opposing effects. In our present climate, the reflection of solar radiation is larger than the heat trapping effects, so the net impact of clouds is to cool the climate system. This could change, however, in the future. If, in response to an initial warming, clouds cause less cooling than they do in the present climate, then this change will amplify the initial warming and be a positive cloud feedback. If, on the other hand, the cooling effect of clouds is increased in a warmer climate, then clouds will act to reduce an initial warming and therefore be a negative feedback. Although the exact answer is uncertain, the best guess of the scientific community is that the cloud feedback is positive, meaning that clouds amplify warming. So what is our planet's climate sensitivity?
As we calculated earlier in this video, the climate sensitivity without accounting for feedbacks is 1.1 Kelvin of warming for doubled carbon dioxide. If we include the net amplifying effects of the feedbacks, we estimate that the climate sensitivity falls into the range of 2.5 to 4 degrees Kelvin. This wide range reflects uncertainty in the strength of the feedbacks, in particular the cloud feedback. Our best estimate of climate sensitivity is 3 degrees Kelvin of warming in response to doubled carbon dioxide. This is a surprising result. It says that the direct warming from carbon dioxide, about 1 degree, is only a third of the total warming. The rest of the warming, 2/3, comes from feedbacks. Make sure you know that for the exam. This places feedbacks in the center of the climate change debate. And now, your moment of dog.